As many of you will know, the most common way to detect a sample, well, an analyte in a biological sample, is to use an enzyme-linked immunosorbent assay, or ELISA. There are several flavors of ELISA, but the one I'm going to be talking about is the so-called sandwich ELISA, the one presented on the right of this slide. In this assay, you use a capture antibody to capture your analyte, and then you detect it with a detection antibody, usually coupled to an enzyme that converts to a substrate, to something you can detect. The limiting factor of ELISAs are their sensitivity or limit of detection. The way you usually detect something in a bulk ELISA or traditional ELISA is that you have your sample presented on the left in the Van der Waals tube, and the signal you're generating from all the detection events is proportional to the concentration of your sample. One way to improve the limit of detection is to use a digital method in which you partition your sample into, let's say, microwells. And you're going to have either 0 or 1 molecule of your sample in each partition. This way, when you detect the signal, you're going to get either a detection event, which is a 1, or no detection event, which is a 0, hence the term digital. From that, you can go, like using Poisson statistic, you can reconstruct the initial, calculate the initial concentration, the initial number of molecules, and get a very good measurement. Of course, in biological samples, things are never that clear, and you're never going to get just 0, 1. You can get multiple events, but let's take an example. On the right, you have a droplet with a bead coated in antibodies. You capture the analyte in blue. You add the detection antibody, which is conjugated to an enzyme, which comes to substrate, and you can get several levels of fluorescence intensity, which is going to tell you if you have 1, 2, or 3 molecules. And this way, you can just as well calculate your initial concentration. There are available commercial systems doing digital ELISA. For example, the CMO system from Quanterix. So here you have what I just showed before, a bead coated in capture antibody. You add the analyte and the detection antibody. And then what you want to do is get each bead in a microwell. So you have 1 bead per microwell. The substrate of the enzyme is then added, and you cover the whole thing with the silicon membrane to prevent evaporation, because you're working with very small volumes. And you can see on the lower right that you end up with a majority of negative, majority of negative wells, and some positive with different intensities. So probably we have 1 and 2 molecules for these different intensities. This system is great. The only problem is that it's very expensive, and it requires a lot of work to do an experiment. Because like I said, you have to cover the wells to make sure they don't evaporate. You have to actually put the beads in the wells. So it's complicated to work. One way to solve that would be to use digital microfluidics, or DMF. DMF is a technique in which you can move very small volumes of liquid on a glass surface automatically without human intervention. How it works is you have a DMF device presented on the top left, and it's schematic representation on the bottom left. So you have a bottom plate, which is glass, covered in a metal, like we have chromium electrodes. This is covered in a dielectric to isolate them from one another. And the whole thing is covered in a hydrophobic layer to let the liquid actually move on top. And then we have a top plate, which is also glass slide, covered in a conductive layer and a hydrophobic layer again to let the droplet move. So when we apply a current to any of the bottom electrodes, the droplet of liquid is going to move to that electrode. How it looks in action is shown on the right on the video. So you can see we can dispense volumes. We can actually move droplet, mix them, split them. And the whole thing, as you can see, on one electrode, we have the electrodes are these little squares. One electrode is around 1 microliter. So we can work with pretty small volumes and actually save regions and work with the volumes that digital ELISA would be good with. So moving on, what we would like to do with this is we have this biological sample. We add functionalized magnetic particles that are meaning magnetic beads with an antibody on top. We capture the analytes we want to analyze. Then we add a detection antibody with that detection method that I'm not at liberty to discuss. And in the end, we have all these beads in a single droplet. We excite the droplet and we can detect the positive ones. And so we end up with zeros and ones. And so we have a digital ELISA with no partitioning because the partition is the bit itself. The limits, like the two points of intention here, are the detection method, because it needs to be sensitive enough, and also it needs to be localized to the bead. And the first step, the functionalized magnetic particles, because we need one binding event per bead. We don't want to have too many. Otherwise, it's not going to be digital. So here I'm presenting some preliminary results about the detection method. So on the left, you can see images on beads under the microscope. The top row, sorry, is bright field. The middle row is Cyanin-3, a fluorescent channel I'm using to detect all beads. So it's the same as the bright field. And the bottom row is Cyanin-5, the channel in which I'm detecting my positive beads only. On the left side is a negative control, and on the right side is a positive control. And as you can see on the bottom row, you can see beads only on the right side, whereas in the middle row, you can see beads in both. And the right part of the figure is a graph presenting the data. So I'm showing the intensity in Cyanin-3 on top or Cyanin-5 on the bottom of a representative bead. And as you can see, all beads, positive and negative, have the same intensity in Cyanin-3, but only positive beads show a strong signal in Cyanin-5. So we can do a digital detection using two fluorescent channels. It works. Now the question is, can we do it with an analyte? And so what I wanted to do is first determine the detection range of bulk ELISA. So as you can see here, we have a traditional plate ELISA, and the limit of detection I observed in this experiment is around 10 picogram per ml. So I went with the same antibodies, the same analyte, and tried to reproduce this with our digital approach. And what I got was not entirely conclusive. So I'm working here with the highest analyte concentration, so the one at the very right on the previous graph, a theoretical number of antibodies per bead of 1,000. Like in theory, we would want one antibody per bead, and I'm still getting a very low signal. So it didn't quite work the first time. And I'm gonna move this so you can see the figure. However, what we can see is that, so on the image on the right, the gray channel is the Cyanin-3, so all beads, and the red channel is Cyanin-5, so in 3 positive signal. And in one, I'm showing something that is the same intensity, like it looks like we have a signal, but the shape of it and the fact that it's as bright in Cyanin-3 and Cyanin-5 tells me it's not, mostly some dust. However, if you look into, we have 2 beads next to each other in Cyanin-3, so in gray, and in red, we have one signal that localizes on the side of one bead. So that could be a positive signal, like a nanolite that we captured and we're detecting. So it's showing some promise, and I'm gonna keep working at it. So what should you remember from this talk about that my experiment didn't work? Well, lowering the limit of detection is key to advance the use of immunoassays for early disease detection and to monitor treatment effectiveness, which is important in the clinic. Also, that a partition-less digital ELISA will allow for easier and faster highly sensitive detection in the lab or at the point of care, and that digital microfluidics allows for near complete automation of the process, which makes it the perfect platform for digital ELISA. And with that, I would like to thank all the people from the lab and thank you for your attention.
Great, thank you very much, Sheldon. So I'll open up the Q&A now. I'm curious, you had mentioned in a previous conversation about a similar approach with different detection methods. I think that was a CAME in 2016. Could you speak to that?
Yeah, so a similar approach was previously made using pyramid labeling. So in this method, what you do is you're using a dye that the HRP, the enzyme-linked detection antibody, is going to convert. And when it's converted, it has a free radical that's going to make it very reactive. And so it's going to bind to whatever's nearby. And this way, you can make sure that your dye is only going to bind to whatever enzyme converted it. There are limits with this approach. The first one is that if your free radical reacts with the catalytic site of the enzyme, it basically shuts down the enzyme, so it doesn't work anymore. And the other limit is the ability to detect the signal. So on the right, I'm showing they're using a flow cytometer to detect positive beads. But the signal is very short-lived, and so with flow cytometry, it works, I suppose. But we tried it with fluorescence microscopy, and it doesn't. You can't really get an image. It's too short-lived. So there are still things that can be improved about this, and that's what we're trying to do: make it more usable, more user-friendly.
Great, thank you. And then on that line, I'm curious. You're saying the goal is near complete automation of the process at the point of care. However, right now there's a 4-hour incubation period. Could you speak to what has to happen between where the process is now and where it needs to be for point of care? Okay,
so yeah, at the moment I'm using very long incubation. The goal is to shorten this time. That could in theory be done, but then the signal would be lower. So the main thing would be to improve the signal so that we can detect with very short incubation times. The other limit for using the point of care would be the detection. Fluorescence detection, like fluorescent microscope, is an expensive piece of equipment. There are some commercial machines like the IncuSite from Sartorius that would in theory allow to do that in a more automatic fashion. Like you put the reagents on the DMF device, you put it in the IncuSite, you press play, and it runs the thing and does the detection. So there are a number of steps. The first step for me would be to just get the actual assay to work.
Great, thank you very much, Sheldon.